In the previous episode, I completed the propulsion system for this electric surfboard. The motor, impeller, and propulsion housing are finally assembled, but even the best propulsion system is useless without a reliable power source. In this episode, I'll build the battery system from scratch and perform the very first power test. The battery is the heart of this entire project. Unlike a standard RC vehicle, an electric surfboard experiences much higher power demand. So instead of simply increasing capacity, the battery has to maintain voltage under heavy load. I chose LG21700 lithium-ion cells. A total of 144 cells are arranged in a 12 series 12 parallel configuration. Series connection determines system voltage, while parallel connection increases capacity and current capability. Each cell is fixed using dedicated holders to improve mechanical stability and simplify assembly. Placing the cells is only the beginning. The next step is one of the most critical parts of the battery assembly. Each series group needs its own voltage sense wire. Instead of using an integrated BMS, this pack follows a drone-style balancing method using an external charger. Connecting the cells is only half of the process. The battery also needs a structure capable of protecting that energy. Since this board is designed to carry a rider, the enclosure has to withstand vibration, shock, and constant exposure to moisture. For that reason, I designed a dedicated CNC-machined aluminum battery housing. The enclosure protects the battery modules while also maintaining precise alignment of every component. Internal spacing was planned to minimize cable interference and simplify future maintenance. Every fastener is installed in sequence to maintain structural alignment and sealing performance. These details may never be seen during operation, but they define the reliability of the entire system. The next step is building the main power cable. This is the section where the highest current flows through the entire system. Reducing voltage drop and heat generation is just as important as making a proper electrical connection. I selected 8 AWG silicone wire and kept the cable length to approximately 50 centimeters. Shorter cables reduce resistance and improve overall efficiency. The pack connects to the propulsion system through an AS150 high current connector. After soldering, every joint is reinforced using heat shrink tubing to improve insulation and mechanical strength. In high power electric systems, reliability is often determined by the smallest details. The final step is installing the top cover. A dedicated groove was machined to accommodate a 2mm O-ring. Instead of relying only on sealant, the enclosure uses controlled O-ring compression to improve sealing while allowing future maintenance. Since this board operates directly on the water, even the smallest gap can become a path for moisture. After assembly, every fastener is checked again to ensure proper sealing pressure. With the battery pack assembled, the next step is creating the charging interface. This build uses a D38999 connector. Rather than carrying the charging current itself, this connector routes the individual balance sensing signals to the external charger. Once charging begins, the first values to check are the charging current and pack voltage. In this test, the battery is charged at approximately 20 amps. The charger confirms that the pack has been assembled correctly and is communicating normally. With the battery complete, it's finally time to install the propulsion system. This unit converts the motor's rotational energy into water thrust. Every mounting point is checked again to ensure proper alignment with the board. Even small assembly errors can increase vibration or reduce efficiency, so the final installation is performed carefully. The final electronic component is the ESC. It converts the battery's DC power into three-phase power for the motor while controlling its speed. This project uses a Hobbywing Max 4 HVESC capable of operating on a 12S lithium battery. Since the controller was originally designed for land vehicles, additional silicone sealing was applied to improve resistance against moisture. It is not intended to make the controller fully waterproof, but to reduce the possibility of water reaching sensitive electronics. At this point, every major component is finally in place. The next step is the moment we've been working toward since the beginning of this project. This is the very first power up of the entire system. Months of design and assembly come down to this moment. The battery, ESC, and motor finally begin working together as one system. Watching the motor spin doesn't tell the whole story. To visualize the airflow, I used smoke. It makes the invisible flow visible. This allows me to verify both the intake and exhaust directions before moving into water testing. Although the real operating medium is water, the airflow pattern provides a quick way to confirm the propulsion system is working as expected. Every workshop check was now complete. The battery, ESC, motor, and a custom-built propulsion unit were finally connected as one complete system. But everything tested so far had only confirmed basic functionality in open air. This propulsion system was designed for one environment, water. As I slowly increased the throttle, the sound changed completely from the ground test. The impeller, which had been spinning almost freely in air, was now working against the resistance of the water, placing a much more realistic load on both the motor and the ESC. With both the ground test and the first underwater test successfully completed, I was able to confirm that the battery and propulsion system were operating as intended. In the next episode, I'll complete the final assembly and put the board to its first real test. If you enjoyed this build, don't forget to like and subscribe. Thanks for watching, and I'll see you in the next one.